Hello students, let us begin with the solutions to your home assignment problems which I have given to you in the last session. First question was, find the area of the region bounded by the curve y square is equal to x and the lines x is equal to 1 and x is equal to 4 with the x axis. Look into the solution to the first problem. The given curve is y square is equal to x. It is a right-handed parabola with vertex 0, 0 at the origin. Therefore, required area is equal to area of the region A, B, C, D. Here you can see it is a right-handed parabola with the shaded region A, B, C, D. X is equal to 1 here at A and x is equal to 4 at B. Therefore, required area is equal to integral 1 to 4 y dx, that is equal to integral 1 to 4 square root of x dx, since equation 1 gives us y is equal to square root of x, that is equal to x to the power 3 upon 2 upon 3 upon 2 with limits 1 and 4. On applying limits, we have 2 upon 3 into 4 to the power 3 upon 2 minus 1 raised to 3 upon 2, that is equal to 2 upon 3 into 8 minus 1, that gives us 14 upon 3 square units as area. Now, look at the solution to the second question. The given curve is y is equal to x square, which is an upward parabola with the vertex at the origin 0, 0. Therefore, required area is equal to area of the region OAB. Here x is equal to 3. The area which is shaded is to be calculated. Therefore, required area is equal to integral 0 to 3 y dx, that is equal to integral 0 to 3 x square dx. On integrating, we have x cube upon 3 with limits 0 and 3. On applying limits, we have 1 upon 3 into 3 to the power 3 minus 0, that gives us 27 upon 3 is equal to 9 square units as area. Now, let us study about how to calculate the area between two curves. Intuitively, true in the sense of Leibniz, integration is the act of calculating the area by cutting the region into a large number of small strips of elementary area and then adding up these elementary areas. Suppose we are given two curves represented by y is equal to f of x and y is equal to g of x, where f of x is greater than or equal to g of x in the closed interval a b as shown in the figure. We have here two curves as y is equal to g of x and y is equal to f of x with a width d of x and y as the height, that is equal to f of x minus g of x. Here the points of intersection of these two curves are given by x is equal to a and x is equal to b, obtained by taking common values of y from the given equation of two curves. For setting up a formula for the integral, it is convenient to take elementary area in the form of vertical strips. As indicated in the figure, elementary strip has height f x minus g of x and width d of x, so that the elementary area d a is equal to f of x minus g of x into dx, and the total area A can be taken as A is equal to integral a to b f of x minus d of x into dx. Now, let us look at one example. Find the area of the region bounded by the curve y is equal to x square minus 6 x plus 5, the x axis and the lines x is equal to 2 and x is equal to 4. For the solution, the given curve is y is equal to x square minus 6 x plus 5, it can be written as y is equal to x square minus 6x plus 9 minus 4. Look here, 5 is written as 9 minus 4. So that y minus 4 can be written as x minus 3 whole square, which represents an upward parabola with vertex at 3 comma minus 4. As the required portion of the curve lies below x axis, y is negative. Therefore, required area is equal to modulus of integral 2 to 4 y dx is equal to modulus of integral 2 to 4 x square minus 6x plus 5 into dx. That gives modulus of x cube upon 3 minus 6 into x square upon 2 plus 5x with limits 2 and 4. That is equal to modulus 64 upon 3 minus 48 plus 20 minus 8 upon 3 minus 12 plus 10. That is equal to modulus minus 20 upon 3 minus 2 upon 3. That gives minus 22 upon 3. Absolute value is 22 upon 3 square units. One more example here. Find the area of the region included between the curve 4y is equal to 3x square and the line 3x minus 2y plus 12 is equal to 0. For the solution, the given curve is 4y is equal to 3x square. Take this as the first equation. It can be written as y is equal to 3 upon 4 x square, which represents an upward parabola with the vertex at the origin 0, 0. We have an upward parabola here with point P minus 2 comma 3 and point Q with points 4 comma 12, and this is the line y is equal to 3x plus 12 upon 2. The given line is 3x minus 2y plus 12 is equal to 0. Therefore, y is equal to 3x plus 12 upon 2. Take this as the second equation. On solving equation 1 and equation 2, we get 3x plus 12 upon 2 is equal to 3 upon 4 x square. That implies 6x plus 24 is equal to 3x square. That gives x square minus 2x minus 8 is equal to 0, which can be factorized as x plus 2 into x minus 4 is equal to 0. That gives x is equal to minus 2 and x is equal to 4. Therefore, the points of intersection are P minus 2 comma 3 and Q 4 comma 12. Therefore, required area is equal to area of the shaded region, that is given by integral minus 2 to 4 into 3x plus 12 upon 2 minus 3 upon 4 x square dx, that is equal to 3 upon 2 into x square upon 2 plus 6x minus 3 upon 4 into x cube upon 3 with limits minus 2 and 4. That gives 1 upon 4 into 3x square plus 24x minus x cube with limits minus 2 and 4. On applying these limits, we have 1 upon 4 into 48 plus 96 minus 64 minus 12 minus 48 plus 8. Therefore, the required area is 1 upon 4 into 108, that is 27 square units. Now, let us look into one more interesting example. Find the area of the region bounded by the two parabolas y is equal to x square and y square is equal to x. For the solution, the point of intersection of these two parabolas are 0, 0 and a, that is 1 comma 1. Here we can set y square is equal to x or y is equal to square root of x, that is equal to f of x, and y is equal to x square is equal to g of x. F of x is greater than or equal to g of x in the interval 0, 1. We can see the two parabolas here, y is equal to x square and x is equal to y square, and the points of intersection as 1 comma 1 and 0 comma 0 at the origin. Therefore, the required area of the shaded region is equal to integral 0 to 1 f of x minus g of x dx, that is equal to integral 0 to 1 square root of x minus x square dx, that is equal to 2 upon 3 into x to the power 3 upon 2 minus x cube upon 3 with limits 0 and 1. On applying the limits, we get a simplified answer as 1 upon 3. Let us see one more example here. Find the area bounded by the curve y is equal to cos x between x is equal to 0 and x is equal to 2 pi. For the solution, from the figure, the required area is equal to area of the region OABO plus area of the region BCDB plus area of the region DEFD. These three shaded areas are to be calculated. Thus, we have the required area is equal to integral 0 to pi upon 2 cos x dx plus absolute value of integral pi by 2 to 3 pi by 2 cos x dx plus integral 3 pi by 2 to 2 pi cos x dx, that is equal to sin x with limits 0 and pi by 2 plus absolute value of sin x between pi by 2 and 3 pi by 2 as limits plus sin x with limits 3 pi by 2 and 2 pi. On applying the limits, we get 1 plus 2 plus 1, that is equal to 4. Another example here, using method of integration, find the area bounded by the curve modulus of x plus modulus of y is equal to 1. For the solution, as the given curve is modulus of x plus modulus of y is equal to 1, take this as first equation, we can write plus or minus x plus or minus y is equal to 0. The required region is enclosed by the lines x plus y is equal to 1, x minus y is equal to 1, minus x plus y is equal to 1 and minus x minus y is equal to 1. You can see in the figure, we have the region AOB with A point as 1 comma 0, B as 0 comma B and AB line as x plus y is equal to 1, BC line with minus x plus y is equal to 1, C point as minus 1 comma 0 and CD line as minus x minus y is equal to 1 and x minus y is equal to 1 as DA. Clearly, curve 1 is symmetrical about both axes x and y. Required area is given by 4 into area of region OAB, that is equal to 4 into integral 0 to 1 minus x dx. Since x plus y is equal to 1, that implies y is equal to 1 minus x, that is equal to 4 into x minus x square upon 2 with lower limit as 0 and upper limit as 1. On applying the limits, we have 4 into 1 minus 1 upon 2 minus 0 minus 0. Therefore, the required area is 4 upon 2, that is 2 square units. So, students, today we learned how to calculate the area between the two curves with some interesting examples. In the next session also, we shall be solving some interesting problems. Thank you.